Okay, so if there are no other questions, we can start our discussion for today. So today I wanted to complete our discussion of the principle of holography of information in asymptotically flat spacetimes. So let me just remind you where we stopped yesterday. At the in yesterday's lecture, we were discussing the kinds of boundary conditions that we should have in asymptotically flat spacetimes, and we wrote down this expansion of the metric. And I just want to remind you, for those of you who've seen this many times before, it may not be required, but for those of you who are seeing this for the first time, there are some terms that we'll use. There are some subleading components of the metric. One of them is called CAB, which is called the shear. And there is the derivative of CAB with respect to U, and that is called the Bondi news. And then there is this other component M, which is called the Bondi mass aspect. These components basically tell you about various components of the metric. The CAB contains the two dynamical modes of the dynamical polarizations of the graviton, whereas this M is some constrained component that basically tells you how much mass is inside at a given point. Okay, so now I want to go on and discuss a little bit the quantum theory. So there's, of course, a lot of literature and a lot of work that has been done on trying to understand gravity in four-dimensional asymptotically flat spacetimes. This is also a topic which has attracted a lot of recent attention. We're going to try and cut a particular path to it so that we can reach the result that I think is relevant for the information paradox in the fastest possible way. I'm going to try and describe what I think are the important results. But of course, there is a lot of other interesting stuff here. And again, I'll refer you to the references and the published notes to follow the literature and find many more interesting topics. So let me just start by saying a few things about gravity in four-dimensional flat asymptotically flat spacetimes. So the first thing I think is that, and the way I like to think of it is that there's some good news and there's some bad news. Okay. So let me start with the good news first. Okay. So the good news is that in a sense, the operator algebra at Scri+ is much simpler than it is in ATS. Okay. So the good news is that the operator algebra is much simpler than ATS. Okay, why is that the case? Okay, so let me give you an example of what I'm talking about. When you quantize a theory, you can always take the Lagrangian, and you can work out what the canonical momenta are compared to some fields, and then you can work out the commutation relations. And usually, when we do this, we do this in some free field approximation, and then we try and work in perturbation theory in that free field approximation. For those of you who've seen how the commutation relations look like in the nonlinear theory of gravity, you know that the Lagrangian in gravity is extremely complicated, because it's root minus gr, and if you try and expand that out in the metric, in fluctuations of the metric, you'll get an infinite sequence of terms in the metric. And therefore, you might have thought that the operator algebra in a theory of gravity would always be extremely complicated, or would somehow be very messy. But one of the beauty of working at Scri+, and this is something that was discovered in the 80s by Ashtekar and others in this program called asymptotic quantization, is that the algebra at Scri+ and also at Scri- simplifies greatly, and a lot of the nonlinear terms in gravity just completely drop out. And so that allows you to derive some exact relations at Scri+. One such relation, for instance, is the fact that if you take this Bondi news operator that I wrote down previously, and you just take the canonical commutation relations that you would get from gravity, then you can work out what these canonical commutators are without setting G Newton to 0. Okay? And you find that that's just it's just something very simple. So there's a sphere delta function there's a derivative of a delta function in U. So notice you have a derivative of a delta function in U. There's a delta function on the sphere. And then there are some terms which come because, the news has to be transverse and traceless. And so there's some metric factors that appear, but these are not particularly, they're not particularly important. If you were to work, for instance, in this holomorphic basis, these factors you could just set to 1 by making the right transformation of basis. But the important point here is that, you do get some factor of G Newton, but you might have thought that, the commutation relations of these operators should be very complicated and should involve all sorts of nonlinear terms. And it is in fact true that, if you go somewhere in the bulk and you try and work out, what is the commutation relation of fluctuations of the metric, you'll get something which is complicated. But that's not the case at Scri+, and you get these extremely simple commutation relations. And the reason is that at large R, the infinite volume of space, this is just the physical reason. Of course, you just work this out exactly. You don't need to use any of these words. But the reason this happens is that the infinite volume causes the nonlinear terms to drop out. Okay, there are other such commutation relations one can derive. I will use some of them later in this lecture. But I wanted to first emphasize this physical and general fact, which is that the operator algebra at null infinity becomes very simple. And there's a similar relation, of course, one can have at past null infinity. This is not special to future null infinity. It also happens at past null infinity. Okay. Now, intuitively, how should you understand? Let me just focus on these commutation relations of the news operators. If you had other dynamical fields in the theory, like a scalar field that we discussed yesterday, there would be very similar relations you could write down. But let me just focus on the graviton, and then I'll say how things generalize to other kinds of dynamical fields. So how should one understand intuitively these commutation relations? Okay, so intuitively, if you look at these commutation relations, you have some metric factors here, and these metric factors are basically meant to ensure that there are only two independent degrees of freedom in NAB and NCD. And what these commutators are basically telling you is that the N and N behave roughly like the derivative of a field of U, okay, of a free field, which is a function of U. Okay, so just to make that a little bit more precise, we can take these commutation relations and we can Fourier transform them. Okay? So let's try and Fourier transform them. So let me define. I was talking about N of U. I could, of course, take the operator and I can Fourier transform it, and I can extract the positive and negative Fourier energy, positive and negative Fourier components. Okay. So I've kept the angle constant, and I've just done a Fourier transform in U. In this equation, omega is always positive, and that's why I've explicitly inserted a plus or minus. I can either take NABU and do a Fourier transform with respect to plus or e to the I omega U, or I can do it with respect to e to the minus I omega U. Okay, and then you could ask, given the commutation relations that we had for the news operators in the previous slide, what do the commutation relations for these Fourier transforms of the news operators become? And that's quite simple to work out. You just need to, so we can just do it together. So let's take n plus and n minus. So let's take n plus, n minus. Okay. And if you work out this commutation relation, you get the constants, which is this I over 16 pi g. You get a square root gamma. You get a delta of omega minus omega prime. These things are just coming for free because, remember, the only thing we've done is we've changed the u coordinate. Okay. So whatever's happening on the sphere just carries over even in Fourier space. Similarly for the tensor indices. Okay. And then the interesting part is what happens in the u coordinate. So we have a factor of e to the I omega u that's coming from this n plus. That's this term. And we have a factor of e to the minus I omega prime u prime. Okay. And then we have a delta function into a delta of u minus u prime, and then we have a du and a du prime. Okay. So I hope everyone can see that this follows from the previous relations that I had. In fact, the only thing that appears inside the integral is this delta function of u minus u prime, and everything else is just going along for the ride. Okay. But this delta function is very easy to integrate. The way we integrate delta functions is we do an integral by parts, and this du goes and hits this. And when this du goes and hits this, you pull down one factor of omega, and then you just set u equal to u prime with the remaining delta function. And then when you do the integral over u, you will also end up setting omega equal to omega prime. Okay? So let me just repeat. First, you do an integral by parts. So you use this du to pull down a factor of I omega. Then you do the u prime integral to set u equal to u prime. Once you've done that, then you have an omega minus omega prime into u in the exponent. And therefore, once you do the other u integral, you just get a delta function in omega minus omega prime. Okay? So this expression, just this last part, just becomes minus I omega into a 2 pi into delta omega minus omega prime. Okay? So let me erase the intermediate line so you can see what the final answer is. Okay? So if you just erase the intermediate line, you will see that the final answer looks very nice and simple. In fact, this I and minus I are going to cancel, so we can erase them as well. Okay. And you see that you've just found that n plus on omega at some point in the sphere with n minus at a different frequency just has a delta function commutation relation with an omega and with a delta function in the sphere coordinates as well. If I were to divide this by 1 over square root omega here, I could take this omega here and normalize these with a 1 over square root omega, and then I would just have a 1. Okay? So this is telling you that when you look at the operator algebra at Scri plus, the operator algebra at Scri plus really behaves like that of a free field. So what are the operators on Scri plus? They're basically polynomials of n and polynomials of other dynamical, the boundary values of other dynamical fields. And this operator algebra really behaves like that of a free field, even though gravity is such a complicated theory, and even though the Lagrangian of gravity is so complicated, and you might have thought that you would have very complicated relations, that doesn't actually happen. Okay? So now that we found this simple operator algebra, one can actually go ahead and also try and construct the Hilbert space of the theory, at least in terms of those states that can be obtained by acting on a vacuum with these n plus and n minus modes, which are the states which have excited dynamical gravitons. So how would one go about doing that? So let us say one had a vacuum which obeyed, we'll just do what we do in QFT 101. So I'm just going through what we do in basic quantum field theory classes. The moment you get commutation relations of the kind that I had in this slide, you know how you should go about and construct a Hilbert space. Well, we should construct a Hilbert space basically by asking that there should be a vacuum, and the vacuum should be annihilated by this n plus. Okay. So we demand that there be a vacuum so that this is 0. Okay. Now at this point, I want to emphasize that there's going to be some bad news about this term. Okay. So for now, the 0 is going to turn out to be a rather complicated object. But for now, let's just assume that we find a vacuum that has this property. We're going to later find that there's an infinite number of vacua that have this property. But let's say 0 is one of those vacua, and you could find a vacua which had the property that was annihilated, and it's annihilated, of course, for omega larger than 0. So we don't talk about these Fourier modes exactly at 0. We talk about these Fourier modes at some non-zero frequency. And they have the property that they annihilate some vacuum state in the theory. If you have that, then of course one can just generate excited states by taking this vacuum and by acting on it with any, with the other modes, with the creation operators. Okay? So if you just acted on the vacuum, this is an example of an excited state. Of course, the state I have written right now is not a state which has a nice and finite norm. So to get a state which has finite norm, I should smear my operator a little bit. And so I'm going to adopt the notation that n of f is just the smeared version of n. So this is just some smeared version of this n operator. In fact, this n of f will have both positive and negative frequency modes when I smear it with some function f. But the positive frequency modes are just going to annihilate the vacuum. And so the only action when I act with this n of f on this 0 state is going to be when these n minuses that sit inside n of f act on 0. Okay? So using this, I can generate actually a Fock space. A Fock space is generated by taking many such smeared functions, acting on it with 0 and taking the span. Okay. As we did previously, when I use the word span, what I mean is you take all possible functions, f1 to fn, you take all possible values of n, and you take the linear combination of all such states that are obtained. And if you do that, you see that from the operator algebra we had previously, you get exactly a Fock space as you would find in any free quantum field theory. Okay, now, as I said, you might have other dynamical degrees of freedom. Sorry, there's a question. In the definition of n of f, we smear n minus. No, we don't only smear n minus, we smear just n. And the reason for that is that n plus, it doesn't matter. N plus doesn't matter because when it acts on the vacuum, it doesn't create any new states. And because the operator algebra of n plus and n minus is so simple, we don't actually have to bother to smear only with n minus. In fact, it's important that we don't, in a sense, it's important that what we're doing is we're taking n and we're smearing it over some compact region. To actually extract n plus and n minus, you would have to, smear the operators over a very large region to extract, to separate the positive and negative frequency components. But we don't need to do that because the positive frequency components just annihilate the vacuum. So you can just take n of f and just act on 0 with it. Okay. So as I said, if you do this, you will get a Fock space. And as I said, you might have other dynamical fields in the theory. Yesterday, one of the fields I discussed was a scalar field. And just like you defined a smeared news operator, you could take the boundary value of a scalar field and you could smear it. Should always put a root gamma. Okay. And you could smear it with some function h. And then the entire space of massless particles that you could construct on this vacuum would be constructed by taking the scalar fields or taking the news operators. And if you had other massless fields, by taking those as well, okay, and by acting on the 0 state. Okay. So this gives the set of all massless excitations that can be built on top of this vacuum 0. Okay. So this is all massless excitations that can be built on top of this 0. Okay, now some of you might be thinking, how did we get a Fock space? Okay, we think the Hilbert space of gravity is very complicated. And how is it that we've got this Fock space? We seem to be finding some nice description of the Hilbert space. When we did ADS, if you remember, we said we have maybe an overcomplete basis. We have some basis where we take these operators, we act from -infinity to infinity. We act on the vacuum with them, and that generates, we said that's a dynamically closed subsector of the Hilbert space. But, we never said that that's, I emphasized at that point how, maybe the inner product could get corrected and it was overcomplete and so on. But here we just really seem to be finding a Fock space. And I'm sure some of you are thinking, how is it that we took this extremely complicated theory of gravity? We didn't even, linearize it. We just kept G Newton on all the time, and we found this Fock space. Okay. So what is happening here? So what's happening here is actually something that you learn when you read Weinberg, again in QFT 101 or 201 or whatever, whenever you read Weinberg. And this one of the points that's emphasized when you do quantum field theory is that the way one should define the S matrix is by talking about two asymptotic spaces. One of them is the in space and one of them is the out space. What we have found here is actually the out space of gravity. Okay, and that out space is defined on Scri plus. Okay, and there is similarly another Hilbert space you could define by taking the operator algebra at Scri minus and that would give you the in space. Both the in space and the out space are Fock spaces. Okay, so both in space and out space are Fock spaces. Both in and out spaces are Fock spaces. But that does not mean that the dynamics of the theory is trivial. Okay? In fact, the dynamics of the theory is extremely complicated, and the dynamics or the S matrix all sits in the change of bases between these two Fock spaces. Okay? So the S matrix is the unitary map that maps the in space to the out space. Okay? But it's important that the S matrix is not trivial, but in this description of the Fock space of the Hilbert space, either at Scri plus or at Scri minus, there is a very simple description, but there are two very simple descriptions. One you can make it past null infinity, the other you can make it future null infinity, and all the dynamics of the theory goes into how you map between those two descriptions. Now, the advantage for what we are going to talk about today is that we only want to talk about information theoretic aspects, where does the information live? And so we will actually not have to bother about the dynamics, and we will be able to exploit this Fock space structure. I mean, it will not be very important. If we didn't have a Fock space structure, we would go back to the ADS-like arguments that we made. Because we are not going to talk about dynamics, and we only want to talk about questions of information localization, we will not actually have to worry about this mapping. That's an advantage and a disadvantage. It's an advantage in some sense because it makes our life simpler. It's a disadvantage in another sense because it means that whatever information we are finding doesn't tell us so much about the dynamics of gravity. And if we want to find some dynamical information, we need to work harder. Okay. So far, what I gave you was the good news. And the only thing I said was that the important point I made was that you can take the full nonlinear theory of gravity in four-dimensional asymptotically flat spacetimes. You can quantize it at Scri plus, and you will get a Fock space. That Fock space is the out space. Okay, good. So now let's turn to the bad. I don't know how bad news it is, but it's the news that makes our life a little bit more complicated. Okay. So far, I have been saying that you take a vacuum, and I call the vacuum 0. And I'm saying, let's now excite states on top of the vacuum.
I'm sorry, can I ask?
Yeah,
can I ask a question before we move on? So we started the good news saying that the algebra is simpler in Minkowski spacetime, right? Yes. But why? And the argument was that at large R, the volume sends the infinite volume sends the nonlinear terms to 0. Right. Why is this not true in ADS? Even there, we have a limit R to infinity, right?
Yeah, indeed, you're right that it's true in ADS, but this is a fact of the it's roughly because if you take the limit if you look at the boundary values, if you look at the boundary of flat space and of ADS, in some sense, in the boundary of ADS, you're only separating things. The boundary of ADS in some sense is some conformal field theory. And there's no meaningful scale you can talk about on the boundary. So there's no sense in which you can separate operator insertions by large amounts on the boundary. And there is a sense in which, there is, let me say this another way. You can see this also in the spectrum. In ADS, even though there's an R tends to infinity limit, in some sense, the spectrum of the theory is quantized. So in a sense, we're living in a box. And it isn't the case that you have these infrared degrees of freedom, whereas here in flat space it is the case that it really is the case that there are physically these very, very low energy degrees of freedom, and so there's a physical sense in which R goes to infinity. In ADS it's true that there's a sense in which you're taking a coordinate R to infinity, but there's also the sense in which the boundary that you're living on is a compact boundary, which is not true here. That being said, one can just take the symplectic form. So this is a computation which one can just do. One can just take the symplectic form in gravity, by the symplectic form, I just mean you take the canonical commutation relations, and you can push those commutation relations all the way to Scri plus in gravity, and you would find that they do trivialize in flat space, and they don't trivialize in ADS. And this has to do roughly with the fact that even in ADS, even though we take an R goes to infinity limit, we live in a compact boundary, which is not true in flat space.
Okay, thank you.
Thanks. Great. Okay, so now what is the bad news in a sense? So the bad news is that this vacuum that we are talking about is infinitely degenerate. Okay. So once again, there's been a lot of work that has gone into this question of analyzing the degeneracy of the vacuum and understanding how it relates to soft theorems. And there's an entire field of research that has done that focuses on this issue and its relation to other physical aspects of scattering and other things. But what I'm just going to try and summarize very briefly what this degeneracy of the vacuum is. Okay. So it turns out that the distinct vacua are labeled by something called the supertranslation charge. Okay. So distinct vacua are labeled by their supertranslation charges. Okay. Now, what is a supertranslation? So it turns out that if you look at a theory of gravity in four-dimensional asymptotically flat space, it in fact has an infinite number of conserved charges, and those infinite number of conserved charges are called supertranslations. By the way, supertranslations has nothing to do with a supersymmetry. It's just a word super because physicists like to use the word super. This supertranslations were discovered before supersymmetry was discovered, so there's no supersymmetry here. Supertranslations are the following objects. We take this Bondi mass aspect, and remember I said that if you integrated this Bondi mass aspect at u goes to minus infinity, you would find the Bondi mass, and in fact at u goes to minus infinity you would find the canonical Hamiltonian. To get the supertranslation charge, what you need to do is integrate this not with the weight 1 on the sphere, but rather with some spherical harmonic. So this is a spherical harmonic. And because there are spherical harmonics that are labeled by L and M, you get an infinite number of supertranslation charges. And one can show that all of these charges are conserved in the theory. Okay. Now, why are they called supertranslations? Let me just tell you what the meaning of the word is. And then I won't have so much more to say about it, but it's again an interesting topic. So the reason they're called supertranslations is the following. Notice that in the formula that I've written down, Q00 is the Hamiltonian. Now, what does the Hamiltonian generate on Scri plus? So the Hamiltonian, remember, generates translations in time. So H generates translations in U. But, the way it generates translations in U is that it translates everything uniformly up in U. Okay? So H doesn't translate one part of the celestial sphere differently from another part of the celestial sphere. So these QLMs you can think of as angle dependent translations in U. So that's why they're called super translations, okay? In that they move some part of Scri plus by some amount and a different part of Scri plus by a different amount. How much they move, one part of Scri plus and the other part of Scri plus depends on which Q you're looking at, which LM you're looking at. Often in the literature, sometimes instead of taking QLM, you take a sum of QLM. So you might talk of Q of F, where you take this Bondi mass aspect and you smear it with some function F. And then the way the super translation acts is determined by this function F. It translates, different parts of the celestial sphere, this omega, by different amounts depending on what you smeared this Bondi mass aspect with. Okay, so that's just to explain the meaning of the term super translation, why it's called a super translation, because the usual translation would just be a translation in U, but this is an angle dependent translation, and that's why it's called a super translation. Okay. Now, we're not so interested in understanding super translations, except for the fact that they make our life slightly harder. And it turns out, therefore, because these vacua are labeled by these super translation charges, in fact, I shouldn't have been writing 0. I mean, I could have been writing 0, but writing 0 was ambiguous. In fact, to specify a vacuum, I need to specify the super translation charges of the vacuum. And so to specify the vacuum, I need to specify a countably infinite set of numbers, which are these SLMs. And this is notation I have introduced. This is notation for the distinct vacua. Okay. The reason I write this curly bracket is basically just to indicate that the vacua are not labeled by one number. They're labeled by giving an infinite, a countably infinite set of numbers, these SLMs for L larger than 1. And you have to give all of these numbers, and then you unambiguously specify a vacuum once you've said that it's a simultaneous eigenstate of all of these QLMs. Okay. So this is a complete, so instead of writing 0, what I should have been writing down was really one of these S vacua. And let me say a little bit more about these S vacua, just to relate it to some more terminology that you might have heard. I'm sure that some of you have heard the terminology that super translations can be divided into, these charges can be divided into a hard part and a soft part. Okay. So what the hard part means is that this is the part which is carried by excitations. Okay. So this is carried by excitations. And this is the part that's carried by the vacuum. So you might often, hear it said that the different vacua are labeled by their soft charges. But notice that for the sake of talking about the vacuum itself, the vacuum doesn't have any other excitations. So on these vacua, the action of QLM is the same as the action of QLM soft. Okay. And the reason for that is that this vacuum doesn't actually have any hard excitations. It's a vacuum. And that's why for this particular set of states, this is not true in general. It's only true for the vacuum. It's not true in general. But for the vacuum, we don't have to bother about making this distinction between hard and soft charges. And we can say the vacuum is specified by super translation charge. This will, in fact, be something that will be physically important for us, because to make this division of the super translation charge into a hard part and a soft part, you need to do an integral over all of u. So you need to see, how you need to, these are defined by different integrals over all of u. They're not just defined at u goes to minus infinity, whereas the super translation charge, the total super translation charge, is just defined by a single integral at u goes to minus infinity. And it's a nice thing, and it will be useful for us that for the vacuum, even though the vacuum you can say is labeled by its soft charges, you can just as well label it by the total super translation charge. Yes, please. Yeah.
So Q soft will annihilate excited states?
Q soft will not annihilate excited states. It will commute with X. So if you have some excitation, which is, it's not annihilate excited states. If you have an excited, an excited state will be built on top of this vacuum. So Q soft will still pick up the soft part of the charge. Q hard will pick up the hard part of the charge. If you're talking about operators, in Q soft will commute with hard operators, but it's not, it will annihilate them. I mean, unless you happen to have S equal to 0, it will not annihilate them.
But okay. So Q soft and Q hard are just are commuting operators.
Correct.
Okay. Thanks.
Okay, great.
So Suvrat, I didn't quite follow. So this QLM is the super translation charge operator?
Yes.
And can I take its expectation value in this S eigenstate?
Yeah, so these, I was saying something about the normalization in a minute. These S eigenstates are delta function normalized. So you have to smear a little bit over S to take its expectation value. But after you smeared with S, you could do that.
Because I had this impression that actually the super translated vacua, actually they had 0 super translation charges, but they could have non-zero super rotation charge.
Why did it have
Maybe
0
it's not-
super? So there's
just because of the, yeah, but I'm not remembering well enough to make a comment. Maybe you can make a comment.
So there isn't a unique vacuum. I mean, the Hilbert space is defined by taking all of these different vacua, all of which have different super translation charges, and by taking a direct sum of all of them. I mean, sometimes people like to talk in terms of this Fock vacuum and dressing the operators and trying to construct super translation eigenstates by some Faddeev Coolidge dressing. But I think it's more.
Yeah, no, this is not. I think what I was referring to is just the classically, if you try to compute the charge, the super translation charge of some state that you got via super translation is just 0. But if you compute the super rotation charge of the same state, it's non-zero. It had something to do with the algebra, but I don't remember the details.
Okay, maybe
I can look it. Yeah.
Maybe we can talk about it later. Sure. Okay. In this situation, I mean, for these vacua, you can. So these vacua.
Hi.
Yes.
I just wanted to make a comment on that previous statement. So
Yes.
because it's simply the fact that super translation charges commute with one another. So if I give you a vacuum, there is no unambiguous way to measure what is the super translation quantum numbers of this vacuum. You can measure whether the super translation quantum numbers have changed. It's the same thing, like you can't measure the phase of an electron. There's nothing known as a phase, and that's because the U1 charge is a billion, but you can measure the changes in the phase. So if I just give you a vacuum state and I ask you to measure what is the super translation charges of this vacuum, you won't be able to give any statement for that. So you have to say you can just measure, you can compare 2 different vacuum states and ask whether they have the same super translation quantum numbers.
Just to say one more. I mean, certainly that's true. But I think, So one would like to have. So I mean, this will again maybe take us into the issues that we were discussing yesterday. In a sense, it's true, of course, that one can't talk about the super translation charge of a vacuum, because unless you have some memory, or unless you have some apparatus that was set in place, you can't say if someone has super translated the vacuum or not. But in quantum field theory, the only way you would be able to frame things, the only way you'd be able to construct a Hilbert space is by declaring that you have these distinct Hilbert spaces and you have these charges. And the charges allow you to, and these charges are labeled by these values of QLM. You're right that in any physical experiment, of course, the only thing you'd ever be able to see is, changes in super translation charges, and that's true. But I don't know of any way in which you could just restrict the Hilbert space so as to talk only about changes in super translation charges and not talk about absolute values of super translation charges.
Yeah, I mean, usually you just select some reference vacuum state. You just choose some arbitrarily, and then you make every decision, every comment you make with respect to that arbitrarily chosen vacuum state. Fine. And then everything is.
Yeah, you could do that. You could just choose something and say, this is the vacuum which has all s's equal to 0, and then everything else has some value of s. Yeah. Okay. So the way I'm using these charges, these vacua, is I'm delta function normalizing them. Okay, so there's a delta. Okay, and so these vacua you need to smear a little bit to make them normalizable states. So we should just keep this in mind. But in any case, about every such vacuum, one can build up a Fock space of the kind that I described previously. And the way one builds up a Fock space, now we need to be careful about the vacuum that we built it up with. So one builds up a Fock space by just doing what we did previously. So you start with some vacuum, and then you act with these smeared news operators. And if you do this, this gives you a Fock space. But now we find that we have an infinite number of Fock spaces. We don't have one Fock space. We have an infinite number of Fock spaces. And therefore, the entire Hilbert space of massless particles is given by taking the infinite direct sum over all of these things of all of these Fock spaces. Okay. So the entire Hilbert space has all of these different soft sectors, and you need to take the direct sum of all of these soft sectors and that gives you the full Hilbert space of massless particles. One question you might have is, why do I need to take the direct sum? Why can't I just work by restricting myself to one sector of the Hilbert space? The point is that if you did that, the S matrix you would get would not be interesting. So many people, including Prahar and others, have done a lot of work on this to show that, if you just try to restrict to one sector of one of these soft sectors, you would not get an interesting S matrix. So it's not like these different soft sectors are super selection sectors, in that if you started with one soft sector at scry minus, you would end up in the same soft sector at scry plus. And to get an interesting S matrix, you really need to take the infinite direct sum of all of these soft sectors. Okay? So this H is now our Hilbert space, and this is what we will call the Hilbert space of massless particles. Okay. So that was, in some sense, the bad news, which is the fact that the Hilbert space we have to deal with is now much more complicated than the Hilbert space we had previously, in that you now need to deal with this direct sum of all of these particles, of all of these Fock spaces. Okay. So now we've actually set the stage to go to our main result. So the main result that I'd like to describe in the next half an hour or so is the following. So I said that we have this Hilbert space, and what I want to now describe is that in this Hilbert space, we have these operators. So we have scry plus, we have scry minus, and we have the past boundary of future null infinity, which is scry plus minus. And the main result I wanted to describe is that in this Hilbert space, any two distinct states can be distinguished in a theory of gravity by observations near scry plus minus. Okay, so the result is that we are now going to try and show, which will actually be very similar to the ADS result, is that any two distinct states in H, these could actually be mixed or pure states in H, can be distinguished by observations near scry plus minus. But I have to make precise what I mean by observations near scry plus minus. So what I'm going to say is they can be distinguished by observations in U in the range minus infinity to minus 1 over epsilon, where this epsilon can be as small as you like. Okay? I want to emphasize that this is very different from the way information would be localized in a local quantum field theory. In a local quantum field theory, you could do the same game of doing asymptotic quantization. You could do this in QED, or you could just do this even for a scalar theory in flat space. And if you did that, you would find that information is not localized near scry plus minus, but rather that you need to look at information over all of future null infinity to be able to extract what the state is. Okay? So in an LQFT, we need measurements over all of scry plus to determine the state. And what I'm trying to tell you is that in gravity, just measurements in this small yellow region are sufficient to determine the state. Of course, I should say that small yellow region is a little misleading, because the small yellow region involves, as you can see here, a semi-infinite interval of U, but it's still not all of U. And the statement is that you can get away by just taking this semi-infinite interval, which is this yellow region, and not having to make measurements on all U to determine the state. Okay? So that's the result that we'd now like to prove. And this is the sense in which we'll try and argue that gravity in 4-dimensional asymptotically flat space stores information holographically. So, at the beginning, a couple of lectures earlier, I said that the principle of holography of information that we were trying to prove was that if you have a Cauchy slice, then there was a sense in which information was available near the boundary of the Cauchy slice. And in ADS, we made that precise by saying that information was available on any time band Here we are saying that information is available here. So this is the boundary of the Cauchy slice. Okay. So in ADS, we didn't have to worry about, we just had a cylinder. You could pick any time band of size 0 to epsilon on that cylinder, and you would be able to, read off the state. Here, that's not the case. You can't just take some cut somewhere here and get all information. But if you were to take the cut here, like this is the boundary of the Cauchy slice, then you can indeed completely identify the state. So that's what we would now like to prove. In fact, the proof will be quite similar to the proof we gave in ADS, so we should be able to do it in the remainder of this lecture. But before I do that, I just wanted to explain what we are trying to prove and how it's very different from the way local quantum field theories localize information. Okay.
Suvrat, there's actually one question by Akhil in the chat. He's asking if super translations are an asymptotic version of the lapse function.
I'm sorry, I didn't understand what that means. The lapse function is usually used as, when you do some 3+1 split, you talk about the coefficient of the dt squared term. I'm not sure what the question means. Maybe if you could elaborate, Akhil.
I mean, it seemed like how you are fixing the initial times, you're describing the initial time slice at u minus infinity, right?
So these are not small gauge transformations. I mean, it's important that these super translations are really physical transformations of the state. So maybe what you're thinking about is the fact that, it's indeed true that you can, we have this notion that in gravity, of course, you can draw your Cauchy slice in whatever way I drew this Cauchy slice right now, but, you could have chosen to draw some part lower and some part higher. And you could have talked about, and indeed, people talk about many finger time where, one part of time evolves faster on one part of the Cauchy slice and slower on another part of the Cauchy slice. But that is a redundancy in description, which has to do with the fact that, small gauge transformations leave the state invariant. These super translations are not small gauge transformations in this sense. They are large gauge transformations that extend all the way out to the asymptotic boundary. So we don't mod out by them. These super translations really take one physical state to another physical state. They're not redundant descriptions of the same physical state. And that's why we had this infinite sum of Fock spaces that we had to consider. It wasn't just that, here's one description and here's another description which is equivalent, but it's rather that there's really a physical symmetry that's acting on the space, which is this BMS group, which is taking one physical configuration to another physical configuration. So these are not redundancies in description, which is perhaps, I think, what you were thinking of. Does that answer the question?
More like an initial condition on the, okay.
It's not this is a symmetry of the theory. So these are some conserved charges that live in the theory. So it doesn't have to do with initial conditions. There really are an infinite number of conserved charges. So you could pick some initial condition and that would give you some value for these charges. But there really are an infinite number of conserved charges.
Okay, thanks.
Yeah, I have a question. Yeah. This is related to the super translation symmetry that you just talked about. So is there any condition on the rate at which this Lie derivative of metric goes to 0 as we approach to infinity? I mean, if I think of this symmetry in terms of the Lie derivative of metric.
So this symmetry at infinity is just acting like f del u. Okay, so there are subleading terms in 1 over r that you need to be careful of, and but if you just go to infinity, the symmetry is just acting as f del u. So in fact, I can tell you how it acts on the fields. It's not growing with r, but it's just acting like f del u. So maybe I could write down an equation. Okay. So if you take this super translation charge and you act on it with this shear, okay, then the action on the shear turns out to be this. Okay. And Prahar, who's on the call, was instrumental in working out this factor of 2. In showing how you would correctly get this factor of 2 when you worked out these commutation relations. But in any case, this is the action of the super translation on the CAB. And you see what it's doing is, we integrated the super translation charge with some YLM. So it's moving these CABs by an amount del U but with some weight which is determined by this omega. So this omega is linked to this omega. Okay? So it's moving it by a spherical harmonic YLM. YLM is just because I chose a basis of spherical harmonics. You could choose some other basis in the sphere. And then there's some inhomogeneous part which will actually be important for us later. But if you just look at what is happening here, what the U dependent part, that's just this. Okay, so it's just doing, this is the translation in U. Okay, so it's just F del U.
Yeah. Okay. Yeah.
On these fields.
Okay. Thanks.
Okay. By the way, I didn't say what TF was. Nobody asked me. This is the trace-free part of DADB. Okay. So this TF means that you take DADB and you subtract off the gamma AB term. So you subtract off the trace. So TF means trace-free. Okay, great. So let's go back to our argument about how information is localized very differently in theory of gravity than it is in an LQFT. So our proof is going to follow two steps. Okay, and the first step is going to be that the vacuum operators. So let me make this a little bit more precise. Okay, so let me define the algebra of operators in minus infinity to minus 1 over epsilon. Let me call this A minus infinity. Okay, this is just a name for A minus infinity. This algebra is an algebra in the sense that we described earlier. You have a News operator, you can multiply, take products of News operators, take linear combinations. You have the Bondi mass, you can multiply that. You might have other dynamical variables. Whatever variables you have at U, you just, by algebra of operators, we just mean you'll consider all possible observations you can make by combining these observables through products and through linear combinations. Okay? So I'm going to call this algebra A minus infinity. And a more precise way to say that any two distinct states can be distinguished by observations in this region is by saying that they can be distinguished by operators in this algebra A minus infinity. Okay? So what I first want to show is that the vacuum operators, which are operators which take you from one vacuum to another vacuum, live in this A minus infinity. So what I want to show is that TSS prime, which is defined as this, is an element of this A minus infinity. So I should say that as I go forward, I'm going to be a little sloppy with these delta function normalized vacua. I'm using these delta function normalized vacua, and I'm talking about these operators that take you from one delta function normalized state to another delta function normalized state. And that's a little sloppy. I should really smear these things out a little bit. But it's just a lot more work and a lot more notation to smear things out. So we'll just work with these delta function normalized vacua. If you'd like to be more careful, you should just smear them out, and it's not hard to do it that way as well. Okay. So the first statement we'd like to prove is that these operators, provided you allow me this delta function sloppiness, live in this A minus infinity. Okay. And this is a step that is unique to gravity. Okay. So in no other theory will it be the case that these operators that take you from one vacuum to another vacuum live in this algebra at Scri plus minus. Okay. So how do you show this? So first, let me remind you that because the super translation charges are defined as U goes to minus infinity, the ADM Hamiltonian is an element of the algebra at U goes to minus infinity. And the reason is, remember, it's an integral of the mass aspect as U goes to minus infinity with the right factors of G Newton and so on. But basically, it's an integral over the sphere of the mass aspect at U goes to minus infinity. So that's why the Hamiltonian itself, or the ADM Hamiltonian, is an element of the algebra at A minus infinity. This is also something that's physical, because if you were to think of this algebra near the past boundary of future null infinity as being the algebra very far away of somebody at the boundary of a Cauchy slice, then one of the facts that we've emphasized again and again in these lectures is that you can measure the energy at infinity, and therefore you can measure in particular this energy. And this Hamiltonian is an element of A minus infinity. Okay? Now, another thing that we emphasized, I should also say that all of these other super translation charges are also elements of the algebra at A minus infinity. Okay? The soft and the hard parts of the super translation charges are not naively elements at A minus infinity. They involve doing an integral at large U. But these super translation charges are also just integrals of this, maybe with the YLM put in here. Right? So they are also integrals of the mass aspect at U goes to minus infinity, And therefore, both the Hamiltonian and other super translation charges are elements of this algebra at a minus infinity, in that there are some observables at a minus infinity. And of course, one should keep in mind the fact that you would need to fix some reference vacuum before you need to fix some reference frame before you can measure these super translation charges. But once that is done, the super translation charges are some observables very far away. Now, the other thing that we have emphasized, that I emphasized also in the ADS lectures, is that if an operator is an element of an algebra, then its spectral projectors are also elements of the algebra. And that's because, if an operator is an element of the algebra, what that means is you can make an observation. And if you can make an observation of that operator and you can determine, what the probabilities of different outcomes are, you also find what its spectral projectors are. You can also observe what its spectral projectors are. So in particular, the projector onto the space of vacua this projector, where I have to do an integral over all vacua, is an element of this a minus infinity. And this is a physical thing. It's the same physical thing that we said in ADS, in that you can measure the energy and you can ask what is the probability that you will get 0. Of course, in doing this, we're being, again, a little careless about IR effects, because if you were to measure the energy, you should never really talk about measuring exactly 0 energy, but you should put some IR cutoff, and you should ask, can I measure the energy up to some IR cutoff? In the next lecture, we'll try and make this a little bit more physical. But for now, we just want to make an operator theoretic argument. And from an operator theoretic point of view, where we don't worry about these IR cutoffs, the projector, if H is an element of a minus infinity, the projector onto the 0 eigenvalues of H, which is the projector onto the space of all vacua, is also an element of this algebra at a minus infinity. Second, given these super translation charges have a set of continuous eigenvalues. So every super translation charge has a set of continuous eigenvalues, and there is a projector you can write down. It's not quite a projector because this is projecting onto a delta function state, but you can write down a spectral decomposition for every super translation charge. What I've written down is not deep. It's just the fact that you take a charge and it has these different eigenvalues. It can have these different eigenvalues, which are S. Okay? And corresponding to every S, there's some delta function normalized operator, which selects states which have that value of S, and that's this PLM. Okay? So this PLM is not a projector, but this PLM is also an element of a minus infinity. If this is the case, then because these algebras are closed under products, you can take this P0 and you can project with all of these PLMs, okay? And you can ask, what is this state? Okay? So what am I doing here? Just so that you don't get lost in the operator theoretic algebra, what I'm doing here is I'm saying, let's make a measurement of these super translation charges. And once you've made a measurement, let's select the case where for the super translation charge LM, QLM, one gets the value SLM. Okay? Now, when one does that, one doesn't project only onto vacua, because remember, I emphasized that these super translation charges had both hard and soft parts. So if one just selects a certain value for the super translation charges, that doesn't mean that one has only the vacuum. It could, this value for the super translation charges could come out of some combination of a background soft charge and a hard excitation. But after doing all of that, if I then project onto the manifold of vacua, which I have done here, then you see that this is just the projector, or not the projector, but it's just this operator that I have on the right side, which is not a projector because of the delta functions, but it selects for you the vacuum with charges SLM, with super translation charges SLM. Okay? So the thing that we proved right now is that this operator can be selected for from a minus infinity. And it's important that both energy projections and super translation charge projections are required for this. And it's important that we are able to project onto the total super translation charge, and we don't have to project onto the soft part of the super translation charge, because that is not directly accessible at a minus infinity. Okay. Okay, so right now we showed that this operator, you can select a particular vacuum from sitting very far away. Okay, and there's a physical procedure in which you can select it. The physical procedure is you make a measurement of the energy in the super translation charges, and you pick only those states where you get some value for the super translation charges and 0 for the energy. And that allows you to select the vacuum. Okay, now this is actually just a selection onto a particular vacuum. In fact, the space of vacua is infinite dimensional and has other operators, including operators that move you from one vacuum to another vacuum. But it's easy to check that in the low energy theory, one can also find such operators in this algebra minus infinity to minus 1 over epsilon. Let me in fact write down such an operator. You see, if you write down this operator, okay, so I'll just write down operator. It might look scary, but actually it's not doing too much. Okay, so this is a shear, is a component of the metric that we talked about. But remember, this component of the metric, doesn't commute with the super translation. In fact, because of this inhomogeneous part that we talked about, it's zero mode can change for you the super translation charge, and you can check that if you start with a given vacuum and you act with this metric operator and then you project back onto the vacuum, this changes for you the value of the super translation charges. So you could have achieved the same effect by using super rotations, but you can also achieve this effect by using just an insertion of the metric. And these new charges are, in fact, can be derived by using the commutation relation I wrote right now. I'll just write down the answer, and those of you who'd like to check it can go back and can check this. The new charges of this new vacuum are just given by into dA dB minus half into L into L plus 1. Okay, so there's some complicated looking formula, but in fact, the complicated looking formula is not so important. What is important is that you can change the value of the super translation charge. Okay, so there are operators. The only physical thing here, okay, the details of this formula you can check, but they're not so important. The physical thing here is that from infinity, if you're at infinity and you're allowed to act with all operators at infinity, and you're allowed to make measurements at infinity, then you can not only select a particular vacuum, you can also make a transition from one vacuum to another vacuum by making a transformation with the metric, by turning on some unitary operator that makes some transformation with the metric, and then projecting back onto the vacuum. And that allows you to go from one vacuum to another vacuum. Okay, so this operator that we've written down takes you from the vacuum S, okay, to the vacuum S prime. Okay. And therefore, we have proved now that because you can both select a particular vacuum, because these operators are part of this A minus infinity. And you see this integral also went only from minus infinity to minus 1 over epsilon. So this operator was part of A minus infinity. Therefore, we have proved that the operators S that cause the transition from S to S prime, or that select onto S and then cause it, move or select onto S prime and then move you to S, that these operators are part of the operator algebra at A minus infinity. Okay, so this is what we just proved. And once again, it might seem like an intimidating statement, but it's actually a simple physical statement. It's just the fact that using the fact that you can measure these charges out at infinity, and using the fact that you can change these charges out at infinity, you can both select and you can cause transitions from these vectors. And I want to emphasize that this is the part that is unique to gravity. In no other theory can you do this. Okay? And that's because once again, it was important for us that apart from these super translation charges, there was a sense in which you could project onto vacua by also measuring the energy, which had to be positive. And so, while it's true that in some gauge theory, you could say, let me project onto all states with charge Q and then maybe move from Q to Q prime. That's not good. That just projects you onto an infinite dimensional space. The fact that you can select a particular state and look at these operators that cause transitions between one particular state to another particular state is unique to gravity and will be very important in the fact that gravity localizes information differently. Okay. Are there any questions about this part? I can take them now, and then we can go on and complete the rest of the argument. Okay, I hope that's because I hope that's not because this was not clear. So if there are questions which okay, actually, maybe we can come. Yeah. You have a question?
Yeah. No. Actually, there's this question in the chat which is asking, can epsilon be arbitrarily large and finite?
Epsilon can be arbitrarily large, but actually I want to think of epsilon as something small. So the question is whether epsilon can be arbitrarily small. I'm going to -1 over epsilon. So I have some semi-infinite interval that extends from some value of u out to -infinity. It doesn't matter what epsilon is, but it's just some, I just want to be able to go from u equal to -infinity to some value of u.
Okay, thanks.
Okay. Was there another question? Or? Okay. So this was the first step, but this is just about vacuum operators. But in fact, we can now find, so the step 2 is to show that all operators, so that map H to H. Remember this, when I write this H, I mean the Hilbert space of massless particles that I introduced earlier. All operators belong to this algebra A minus infinity. Okay, so how do you complete this argument? You see, to complete the second part of the step, you need to repeat this Riech-Leader argument that we made in ADS. Let's try and repeat the Riech-Leader argument. I'll go through it fast because we already spent a lot of time discussing this. If there are questions, I'll be happy to answer them, but let me just go through it fast and hopefully it should be clear. Okay. Remember, I said that you can produce these states by taking, say these smeared news operators, and I'm going to suppress these sphere directions. So there are no, notice that NAB is actually a function of u and omega, but the omegas are just going along for the ride. So I'm going to avoid writing them. Okay. So remember that we said that you can generate these states by starting with this, with some vacuum. Oh, what happened? Starting with the vacuum. And then doing some integrals. And these integrals went from -infinity to infinity. So you could take the news operators, and in the first part of this lecture, I said you smear them with some functions so as to get states of finite norm, but these functions are arbitrary functions, right? And it's important they're arbitrary functions, because what do these functions correspond to? These functions correspond to the fact that you might have an excitation that's somewhere here. The excitation might be localized here. So it's important that this function be allowed to have like support everywhere. We are not talking about excitations that are here. You could have some, an excitation which is here corresponds in the local quantum field theory to some particle that enters here that has a trajectory of this kind. Okay? So that maybe there's some particle that was created at this point in the middle, and then it goes out and it exits Scri plus, or it reaches Scri plus at this point. And this is the state that would be described by F having support in this region. Okay? So in principle, we said we have these states, and these states are described by taking N, smearing it with F, and acting on the vacuum. But as we know now, and as we have seen many times, you can, by using the entanglement that is present in the vacuum, we have the result, and I'll just prove it once again, but we have the result that if you start with one of these vacua, and in fact, this result, as I've emphasized many times, you don't even need gravity. This result is just a result which works in any quantum field theories also. You can take the span of states obtained by acting with these arbitrary ends, and you can generate them by acting with functions that have support only in the interval -infinity to -1 over epsilon. Okay. So even though you can start with functions fi which have support in -infinity to infinity, if you act on the vacuum, you consider the span of states as obtained by acting on the vacuum with all such functions, This is the same as the span of state sets obtained by acting with functions in support -infinity to -1 by epsilon on the same vacuum. Let me just go through the proof again. The proof is going to be very similar. It's going to use the positivity of energy. I'll just do the proof. I'll just remind you of the proof for one particle states, and then the generalization will be the same that we did in ADS. So I won't go through that explicitly. Let me just show you why this is true for states where you act with a single insertion of n of f on S. Okay. So let's psi, we'll prove this by contradiction for single particle states. Let psi be n of f on some vacuum S. Okay. So this is an excitation of a single graviton, which could be anywhere on this state S, on this vacuum S. And let's assume that the state psi is orthogonal to all states that you can get by acting with between -infinity to -1 over epsilon. If it's not orthogonal to, if the state is, if there's no part of the state, if there's no state you can get by acting in the larger interval that's orthogonal to some states you can get by acting in the smaller interval, that means that, the two Hilbert spaces are the same. If these two Hilbert spaces are distinct, there must be one vector that belongs to the larger Hilbert space that's orthogonal to all vectors that belong to this other Hilbert space. So I'm going to make this proof by contradiction and assume that psi n of f tilde is equal to 0, okay, for all f with support. Okay, so let's say this was the case. So let's say the assertion on top was wrong. If the assertion on top was wrong, this is how it would be wrong, right? There would be some state psi which you could produce by acting with n of f on S, and it would be orthogonal to all states you could produce by smearing n over a smaller interval and acting on S. Okay. Now, if this is the case, then it must be the case that psi n of u and the state S is equal to 0 for all u in this interval. Right? This is the only way psi could be orthogonal to all functions when you smear with arbitrary functions in this region. The only way it could happen is if this matrix element was 0 for all u in this region. But now let's take this matrix element, and maybe the theory of quantum gravity that we have is very complicated string theory, but in the end, the rules of quantum mechanics still apply. And there's some set of complete energy eigenstates that we can insert in this matrix element. Okay? And this must also be 0 for all u. But now in this basis of complete energy eigenstates, it's very easy to understand what n of u is. This is just n of 0 on S with e to the I EU. Okay. So this is just simple algebra. And now you notice that this expression, we said it's 0 for all u in -infinity to -1 over epsilon, but it's clearly analytic when u is extended in the upper half plane. But, if you have such a function which vanishes between -infinity to -1 over epsilon, it's analytic for u everywhere in the upper half plane, and it's easy to show that it in fact has to vanish for all real u. Okay? So therefore, this means that psi n of u S is equal to 0 for all u in -infinity to infinity. But now we're in trouble because we argued in the beginning that psi was of the form n of f, right? So psi can't have a 0 inner product with n. It can't have 0 matrix elements for all insertions of u, because remember, if I smear this with f of u, I should get 1, or I should get integral of f squared. So if I smear this left-hand side with f of u and do an integral, I should get psi. And therefore, it's absurd that the matrix element of psi and n of u and S is 0 for all u. This last statement I wrote is absurd. And that's why you cannot have, this assumption must be wrong. And such a state psi cannot really exist in the Hilbert space. So that is the proof for one particle states of this statement. You can make a similar proof for multi-particle states by using the edge of the wedge theorem as we did previously. Okay. Are there any questions about this part? And all we assumed here really was the positivity of energy in the full theory of quantum gravity.
Suvrat?
Yeah.
Actually, I do have. So here we have showed that for all psi, there exists an operator n with n of f.
Yes.
Such that psi vector, sorry, scalar n of psi is n of s is 0. Sorry, is not 0.
Yes, is not 0. Yes.
But can you repeat how does it tell that any psi is can be written as n of f s?
You see, if it was the case that there was some psi which could not be written as, so let's say there was some, I assumed here that you can't have it 0, but let's say there was some psi which could not be written as any n of tilde s, right? So then I can just subtract off the part which can be written as n of tilde s, and I can look at the part which is orthogonal. And so, the only way you can have one vector in a Hilbert space which cannot be written as a linear combination of other vectors in another Hilbert space is if there is some vector in this Hilbert space that's orthogonal to all vectors in the other Hilbert space. So, if it is the case that one Hilbert space doesn't have any vector that's orthogonal to another Hilbert space, then those two Hilbert spaces must be the same, or at least one must be densely, one must densely approximate the other. Because the only way these two Hilbert spaces, if this Hilbert space was larger, then it would have to have some vectors that are orthogonal to all such vectors here. Right? So that's the only way it could be larger. You can always subtract off the parallel part. And the only way there's some vector here that you cannot write as something here is if there's some linear combination of vectors of this kind, which is just orthogonal to a linear combination of vectors of this kind.
Oh, yeah. Okay.
Yeah. Okay.
Yeah.
Maybe we can talk more again if it is not clear.
Okay. Thank you.
Okay. Fine. So now let's just put everything together. In fact, we're almost done. So I emphasize once more that the thing I just said right now about the span of the larger space being the same as the span of the smaller space is true also in a local quantum field theory. But now I want to argue that all operators, so h to h can be written in this algebra at a minus infinity. So let's take some operator. Let A be an operator that maps h to h. Okay. So if it is such an operator, it must have an expansion in this Hilbert space of massless particles. So it must have some expansion with some coefficients and this is a state. So this is a state in HS. This is a state in HS prime. Remember, H was the direct sum of all such Hilbert spaces. So this M of S prime is a state inside S prime. N of S is a state inside H of S. What I'm doing here is nothing. I've just inserted a complete basis of states. And I've said, if you have an operator A, then you can write it in terms of a complete basis of states. N of S runs over a complete basis of states because I sum over both N and S. So I sum over all excited states in HS. And M of S prime also runs over a complete basis of states because I sum over M and S prime. So obviously any operator that goes from H to H can be written in this form, can be expanded in this form. Okay. But now remember, by what we just proved, this operator can be written as the action, or this state can be written as the action of some operator that belongs to this A minus infinity on S. This is what we just showed. We showed that you could get any state by acting with some operator in A minus infinity on S. And same for this M. Right? So we just showed this. Therefore, you can write this operator in this form. so far, actually, we haven't done anything. Even though this is an unusual form, this form also holds in a local quantum field theory. And as we have emphasized many times, this does not by itself allow us to get information. So this equation on the board also holds in an LQFT and does not tell us that information lives near a minus infinity, because you have these operators SS prime that are not part of a minus infinity in a local quantum field theory. But of course, in gravity, the special part is that not only xn and xm, but also this operator that lives in the middle is part of a minus infinity. Let me just copy it. Okay. This expression you could have written always, but now I can write this as xn into what I was calling TSS prime and xm dagger. And all these three are elements of a minus infinity. And this is the part that's special to gravity. And therefore, what we have here is a linear combination of a product of three elements from this algebra. And therefore, this operator belongs to a minus infinity. Okay. So we've actually proved that all operators that map the space of massless particles back to itself have a representation in terms of operators that live near the past boundary of future null infinity. And therefore, it's clear that if you have any distinct states in this Hilbert space of massless particles, they can always be identified by some operator that maps the space of massless particles back to itself. And therefore, they can be identified by observables in a minus infinity. Okay, so let me say a few more things about this. I should say once again that, once again, this discussion today might have been a little bit formal. And so in the next lecture, we'll try and lighten the discussion and just try and work some of the physics out within the context of effective field theory, where we won't talk about von Neumann algebras or anything formal. But let me just emphasize a few aspects of this discussion. You see, one of the questions you could have asked is, this discussion that we did, everything we did right now was in the context used some properties of the low energy theory of gravity, used some properties of what we understand about the asymptotic quantization of gravity. So I want to emphasize what were the assumptions that we required. Okay. So the assumptions that we required were that the vacuum operators belong to a minus infinity. This is not an assumption if you just look at the asymptotic quantization of gravity, but if you have some assumption, if you have some full theory of quantum gravity, then what we required, well, it was not quite an assumption, but it would be an assumption if you have some assumptions to extend the result to a full theory of quantum gravity. So what we will require is that the vacuum operators, we have this family of vacua, which we expect will also be there in string theory, because you already see them in low energies. And what we will require is that the vacuum operators continue to be accessible between minus infinity to -1 over epsilon. And this assumption is the assumption that the full theory shares some low energy properties of what you get by just doing canonical gravity. So it shares low energy properties of the low energy theory. And that's what we expect that. Right? We expect that if we determine something about low energy physics by looking at gravity and looking at the world around us, then there might be some string theory or some very complicated UV completion of this theory, but we are only saying something about the vacuum operators, and provided the full theory shares the low energy properties of low energy gravity, this result will extend to the full theory. And there's another assumption that we needed, which we needed for this Riesz-Leiter theorem, which is the positivity of energy. Okay. Sometimes, this assumption is not even stated explicitly because it's expected, but we do require that the full theory, whatever it is, has some notion of positivity of energy. And of course, when I say positivity here, I just mean that the energy has to be bounded below. And we needed that for making this analyticity argument that we made in the last step. Okay. So provided these two assumptions hold, or provided that the full theory of quantum gravity, whatever it is, still has a spectrum which is bounded below, and it shares some low energy properties of the low energy theory, we would be able to argue that even in this full UV complete theory, without knowing its details, that it has to store information in the way that we described. And just to emphasize, what we proved was that if you look at the past boundary of future null infinity, this boundary here, then all information is available here. Okay. Of course, I should say that a similar result, so we proved that a similar result holds for the future boundary of past null infinity. I mean, you could just have gone through every step I made and performed every step on past null infinity, and you would find that a similar result holds here. Okay. Is also here. But as I said, even though these two parts look like they're very close in the Penrose diagram, in fact, in some sense, they're infinitely far away. And while it's true that one could extract information both from the past boundary of future null infinity or the future boundary of past null infinity, the mapping between them has to do with dynamics. It's not just an information theoretic question, and that's not something that we have said anything about at all. Okay? I should say one more thing about massive particles. As I said at the beginning of this discussion, it would be very nice to be able to extend this discussion to massive particles. But of course, as I said, for black holes, which are very big, if that's what we're interested in, most of the radiation comes out in terms of massless particles. But even if you had massive particles in the theory, one can trace out, one can work out what the structure of the Hilbert space is still a Fock space, and one can trace out massive particles to obtain a mixed state on H. And then everything we said would be true about this mixed state. And by H here, I mean, again, the space of massless particles that we've been talking about. Okay? Finally, I should say something about other dimensions. The reason we restricted to 4 dimensions is because the structure of the vacua in higher dimensions is not as well understood. This is just, I think, a limitation of our own understanding of how gravity works in higher dimensions. But I want to emphasize that in this entire story that we did in 4 dimensions, the fact that you had these super translation, these different vacua labeled by these super translation charges was a complication that we had to deal with, which we found we could deal with. And if in higher dimensions, the correct way to describe the theory is that one can think about a unique vacuum like one does in ADS, then of course that would make life simpler. But even if in higher dimensions, as is expected by many people, you have an infinite degeneracy of vacua, provided those vacua are still labeled by operators in this A minus infinity in this region here, provided the vacuum operators all live in this past boundary of future null infinity, even in higher dimensions, we expect that this argument would go through. But of course, we can only make it once we understand that vacuum structure better. Okay, so actually, I think we are done. We are also out of time. So I'll stop here. And as I said, next time, we'll try and make this more physical, and we'll come back and relate this back to the information paradox. But this concludes our discussion of this general principle of holography of information, which in general, as I said, is the statement that information in a theory of gravity is localized very differently from LQFTs and is stored in the boundary of a Cauchy slice. And we made that precise in 2 different ways, in ADS and in flat space. So let me stop here and let me ask if there are questions. There are no questions in the chat also. If there are no questions, then I worry that everything I've said has been very unclear.
Excuse me.
Go on, yeah.
Go ahead, please.
Could you repeat the argument about the massive particles, please?
Yeah. So I said that what we said was true for massless particles. So it was true for this Hilbert space H. But let us say it. I said 2 things. First is that if you take a very large black hole, then you expect that if it's provided its radius is very large, the temperature is the inverse of the radius. And provided the temperature is smaller than the smallest massive particle, most of the radiation will be emitted in terms of massless particles. And therefore, for big black holes, this may not be as bad as bad an assumption, or not an assumption. It may not be as much of an omission as it might have been otherwise. And so, it is an omission that we are not able to talk about massive particles, because, as I said, massive particles don't live on null infinity. They end up here on future time like infinity and start their life at past time like infinity. So first I just said something about why it's not such a serious omission. But the other thing I said was that, you can quantize these massive particles. So we do understand how to do asymptotic quantization for them as well. And the Hilbert space has, again, the structure of a Fock space. But you can trace out the space of massive, you can trace out the degrees of freedom, these massive particles. And if you did that, there would be some entanglement between the massive and the massless particles. And you would, in general, get a mixed state for the massless particles. So, the state for the massless particles would not be a pure state, it would be a mixed state. And of course, we couldn't say anything about the state of the massive particles, but we can determine the mixed state of the massless particles. If you go through the argument I said previously, you can also distinguish all arbitrary mixed states of massless excitations. So that's the amount of information we can get. So, if you have massive particles, what we said right now, what we showed right now is that you should be able to trace, you trace them out, you get a mixed state of massless particles, and you can get information about that. That being said, maybe there's some clever way to get information about massive particles also, but we have not described that. Does that answer the question? Or?
Yes, thanks.
Okay, thanks. Yeah. There was another question, I think.
Yeah, I actually also had a question about these massive particles. It's maybe because if we look at this this holography at no infinity, if I can call it that way, and we see it as a holographic theory. We know from for example ADS that in a mixed state we get some quantum extremal surface. I was just wondering if we have a mixed state for the here on the boundary, could we maybe also expect this, such a quantum extremal surface, or maybe even sort of a horizon or something?
Yeah. I mean, this mixed state was actually is occurring because I traced out some degrees of freedom that live here, like these massive particles. So even if the full state of the theory was pure, I was just saying there's some information that it looks like it's very hard to get from null infinity, which is information about massless particles. And that's why I was saying there's a mixed state. I'm not sure there's a geometric notion of a horizon that's associated with that. I mean, it's true that sometimes if you have a mixed state, there's a sense in which you have a horizon, but here I'm not sure there's a horizon or some part that you can't look beyond. It's true that you can't see what's. I mean, there's some degrees of freedom that you can't keep track of, that we are not keeping track of, and you can't see those. But I'm not sure that there's a horizon that's associated with them. I don't know of any way to think of it in terms of a horizon. I mean, a mixed state would occur just if you traced out some degrees of freedom, and it's maybe there's a clever way to think of it in terms of horizon, but I don't know what that is. I mean, another way to think of it is you could just think of a you could just think of a theory of gravity which has. Let me also say one more thing about ADS. In ADS, we could have had the same kind of complication with massive particles. The thing that saves us in ADS is the fact that when we don't say it often, but it's true that the massive particles that we consider in ADS all have a mass that's proportional to the cosmological scale. So they really have very, very, very low mass compared to, electrons or other particles that we are talking about. Electron doesn't have a mass that's inverse cosmological scale. So in ADS CFT, when we usually talk about massive excitations, we're talking about particles whose mass scales with the cosmological scale. And that's the reason they're easy to deal with. In fact, if you started looking at particles whose mass was parametrically larger than the cosmological scale, even in ADS, it would be hard to, not impossible, but hard to extract information about them from the boundary. And in a sense, that's what's happening here. The cosmological scale the energy scale has gone off to 0. And so massive particles just die off exponentially fast. They don't die off like a power law as they do in ADS. And so if you have some black hole or you have some particles in the bulk, and there's some entanglement between the massless and the massive particles, using the formalism we currently described, you would not be able to tell what the state of the massive particles was. But you could hope that entanglement was small and most of the information was in massless particles.
Suvrat, there's a question in the chat.
Could you please expand a little bit on why the different vacua labeled by supertranslation charges are not in different superselection sectors? Is it related to the fact that there are no local gauge invariant observables in gravity? No, it's actually just a dynamical question. It's a fact that, if you try to say that we live in only one superselection sector, which is just one soft vacuum, then remember that the supertranslation charges are conserved. So you start with some state on past null infinity, and the state on future null infinity has the same supertranslation charges. But now you said, let's say you decided I want to focus on the vacuum which has 0 supertranslation charge. So I want to focus on a particular vacuum. If you do that, then the hard charge has to be conserved by itself, because the soft charge is just fixed by fiat, and the hard charge has to be conserved by itself. And if you do that, the S matrix will trivialize. If you fix the hard charge, you just end up fixing the final state. So if you want an interesting S matrix, you have to allow, the fact that particles of one kind of energy from one kind can scatter into particles of a different kind. The hard charge changes in that, and that's compensated by some change in the soft charge. And that's how you get an interesting S matrix. So dynamically, evolution from Scri minus to Scri plus doesn't keep you within one superselection sector. I hope that answers.
I have one question. So one of the assumptions you wrote in the last page is the vacuum operators belongs to A infinity, even the full UV complete theory.
Yes.
Can you explain why do we expect our asymptotic symmetry group? Yeah.
Yeah, good. So you're right that the asymptotic symmetry group might be enlarged. It could be maybe that the vacuum operators are not labeled only by supertranslation charges, but you require other charges to label the vacuum operators. But provided all those charges live at A minus infinity or live at infinity, the argument that we had would still go through. So we are not actually assuming that the asymptotic symmetry group is not changed. Although we would expect that if you analyze the low energy theory carefully enough, you should see what the symmetry group of the UV complete theory is. But we are only assuming that whatever charges there are that label the vacua are accessible at infinity. And that's a good assumption, because that's an assumption about low energy physics. It's telling us that there are no, the UV complete theory, usually the way we think about it, or you think about string theory, is it adds on some spectrum of massive particles and adds on some kinds of interactions. And those interactions, which become important at high energies, change the physics at high energies. But you don't usually expect that they change the vacuum physics drastically. You don't usually expect, that's what we expect from effective field theory. And so the argument here is just a physical assumption of effective field theory that if you study low energy gravity carefully enough, you will determine the correct properties of the vacuum and transitions between the vacua. But you will not be able to determine what's happening at high energies, but we don't need that to make this simple information theoretic argument about information localization.
Okay, yeah, thanks. Okay.